Imagine you have a map, any map. Could be the countries of Europe, the states of Brazil, the provinces of China. Now grab some colored pencils and try to color every region so that no two regions sharing a border get the same color. How many colors do you need? 5? 6? 10? What if I told you the answer is 4? Always 4. No matter how twisted, how insanely complicated your map is, 4 colors will always be enough. And what if I told you that proving this took over 100 years, destroyed careers, embarrassed some of the greatest mathematicians alive, and ultimately required a computer to finish the job? A move so controversial it forced mathematicians to ask a question they'd never had to ask before: what actually counts as a proof? This is the story of the 4-color theorem. Let's start where every good math story starts, with someone doodling. In 1852, a South African mathematician named Francis Guthrie was coloring a map of the counties of England. He noticed something. No matter how he arranged the colors, he never seemed to need more than 4. So he asked his brother Frederick, who was studying under the legendary Augustus de Morgan in London, "Is it always possible to color any map with just 4 colors so that neighboring regions get different colors?" De Morgan loved the problem. He wrote to William Rowan Hamilton about it almost immediately. Hamilton, famously, did not care. He wrote back saying he didn't plan to work on it anytime soon. He should have, because this deceptively simple question would go on to consume mathematicians for the next century and a half. But before we dive into the history, let's formalize what we're actually asking. Because coloring a map sounds like kindergarten, but the mathematics underneath is razor sharp. Take any map and convert it into a graph. Every region becomes a vertex, a dot. If 2 regions share a border, not just a point, but an actual line segment of border, you draw an edge between their vertices. What you get is called a planar graph, meaning you can draw it flat on a piece of paper with no edges crossing each other. The 4-color conjecture then becomes a statement about planar graphs. Every planar graph has a chromatic number of at most 4. The chromatic number is the minimum number of colors you need to color all vertices so that no 2 connected vertices share a color. Now here's what makes this problem so seductive. Proving that 5 colors suffice? That's almost trivial. A talented undergraduate can do it in an afternoon. But going from 5 down to 4, that tiny step took the combined efforts of hundreds of mathematicians and over a century of work. Let me show you why. The 5-color proof relies on a beautiful structural fact about planar graphs that comes straight from Euler's formula. You know Euler's formula for polyhedra: vertices minus edges plus faces equals 2. V minus E plus F equals 2. This holds for any connected planar graph if you count the outer infinite region as a face. From this formula, you can derive something crucial. Every planar graph must contain at least 1 vertex with degree 5 or less, meaning there's always at least 1 region on your map that touches 5 or fewer neighbors. Why? Suppose every vertex had degree 6 or higher. Then the sum of all degrees would be at least 6v, and since every edge contributes 2 to the total degree count, we'd get E is at least 3v. But Euler's formula, combined with the fact that every face is bounded by at least 3 edges, gives us E is at most 3v minus 6. Contradiction. So somewhere in your graph there's a vertex connected to at most 5 others. Now here's the 5-color argument. Take your planar graph. Find that vertex with degree 5 or less, call it V. Remove it. By induction, the remaining graph can be 5-colored. Now put V back. If V has 4 or fewer neighbors, you have a spare color available, so just assign it. If V has exactly 5 neighbors, and they're using all 5 colors, you need a cleverer trick. You look at 2 non-adjacent neighbors of V, and because the graph is planar, you can always find a pair, and you swap colors along a connected path between them to free up a color for V. Done. 5 colors. Always works. Beautiful, clean, elegant. So why can't you just tweak that argument for 4 colors? Alfred Bray Kempe thought he could. In 1879, Kempe published a proof in the American Journal of Mathematics that 4 colors always suffice. The mathematical community celebrated. The problem was solved. Kempe was elected a Fellow of the Royal Society, partly on the strength of this result. For 11 years, his proof stood unchallenged. Then, in 1890, Percy Heawood found the flaw. Heawood showed that Kempe's argument broke down in a very specific case. Kempe's strategy involved what we now call Kempe chains, paths of alternating colors connecting certain vertices. When V has 5 neighbors using all 4 colors, Kempe needed to perform 2 simultaneous color swaps along 2 different Kempe chains to free up a color. The problem: those 2 chains could interfere with each other. Swapping colors along one chain could disrupt the other chain, creating a conflict. Kempe assumed the chains were independent. They weren't always. Heawood constructed an explicit counterexample where the chains tangled and the whole argument collapsed. But here's the twist. Heawood's refutation didn't produce a map that actually needed 5 colors. He only showed that Kempe's proof was wrong, not that the theorem was false. The conjecture itself remained standing, unkilled. And Kempe's chains, despite the failed proof, turned out to be one of the most important ideas in the entire saga. Every subsequent attack on the problem would use them. After Heawood, mathematicians tried everything. Some tried to find a counterexample, a map requiring 5 colors. Others tried to prove 4 sufficed using new techniques. For decades, the problem resisted both approaches. George David Birkhoff made significant progress in 1913 by introducing the concept of reducible configurations. Here's the idea. If you can show that a certain subgraph pattern, whenever it appears in a planar graph, can always be replaced by something simpler without affecting 4-colorability, then that configuration is reducible. You don't need to worry about graphs containing it. You can shrink them down and handle the simpler case. The dream strategy became clear. Find an unavoidable set of reducible configurations. An unavoidable set is a collection of subgraph patterns, such that every planar graph must contain at least one of them. If every pattern in that set is also reducible, then you've proven the theorem by a kind of structural induction. Every planar graph either is small enough to 4-color directly, or it contains a reducible configuration which lets you simplify it, and you keep going until you're done. Simple concept, nightmarish execution. The unavoidable sets people could construct were enormous, and proving each configuration reducible required exhaustive case analysis. Hundreds, sometimes thousands of subcases. By the mid-20th century, it was becoming clear that if the 4-color theorem was true, the proof might be too large for any human to check by hand. Enter Kenneth Appel and Wolfgang Haken at the University of Illinois. In 1976, they announced something unprecedented, a proof of the 4-color theorem that relied essentially on a computer. They had constructed an unavoidable set of 1,936 reducible configurations. For each configuration, they wrote custom programs that checked through hundreds of hours of computation on an IBM 360 mainframe that every single one was indeed reducible. The human verifiable part of the proof, the theoretical framework, the construction of the unavoidable set, the algorithms, filled several hundred pages of journal articles. But the core verification, the part that actually clinched the theorem, was performed by a machine. The mathematical world split in two. Some mathematicians accepted the result. The logic was sound in principle. If the unavoidable set was correct, and every configuration in it was genuinely reducible, the theorem followed. The computer was just doing what a human could theoretically do, only faster. Others were deeply uncomfortable. A proof is supposed to be something a human mind can survey, comprehend, and verify. If no person could realistically check all 1,936 configurations by hand, and the computer code itself might contain bugs, was this really a proof in the traditional sense? The philosopher Thomas Timotsko argued that the Appel-Haken proof fundamentally changed the nature of mathematical knowledge, introducing empirical uncertainty into a domain that was supposed to be purely deductive. And the concerns weren't just philosophical. Appel and Haken's proof was genuinely difficult to verify. The computer programs were complex. Small errors were found and corrected over the years. The unavoidable set went through revisions. The mathematical community never quite achieved the level of confidence in this proof that it had in, say, Wiles's proof of Fermat's last theorem. So others tried to do better. In 1997, Neil Robertson, Daniel Sanders, Paul Seymour, and Robin Thomas published a significantly simplified proof. They reduced the unavoidable set from 1,936 configurations down to 633. Their computer verification was cleaner, more structured, and independently checkable. They even made their code publicly available so anyone could run it. This was a major step forward, but it was still a computer-assisted proof. The fundamental philosophical question remained. Then in 2005, Georges Gonthier and Benjamin Werner did something remarkable. They produced a formal verification of the four-color theorem using the Coq proof assistant. Coq is a system where every logical step is machine-checked against a tiny, trusted kernel of formal logic. It's not just running a program and trusting the output, it's constructing a complete formal proof object that can be independently verified down to the axioms. Gonthier's formalization didn't just check the 633 configurations. It formalized the entire mathematical framework: graph theory, planarity, reducibility, the construction of the unavoidable set, in rigorous type theory. The proof was about 60,000 lines of Coq code. Was this finally satisfying? For many mathematicians, yes. If you trust the Coq kernel, and it's small enough and well-studied enough that most logicians do, then you have a proof whose correctness doesn't depend on any human's ability to hold the whole thing in their head. The chain of trust goes axioms, logical rules, tiny verified kernel, then the full proof built on top. It's arguably more reliable than most human-written proofs in mathematics, which routinely contain small gaps that experts fill in mentally. But it still bothers some people. And honestly, I think it should bother you a little bit too, not because the theorem is in doubt, it's proven, full stop, but because of what it says about the landscape of mathematical truth. Think about what happened here. We have a statement that a child can understand. 4 colors suffice for any map. We have overwhelming empirical evidence. Nobody has ever found a map needing 5. We have a proof, multiple proofs, in fact. But no human being has ever sat down and verified the complete proof from start to finish using only their mind and a pencil. The theorem lives in this strange territory where we know it's true. We have every reason to believe it's true, but the only path to certainty runs through silicon. The 4-color theorem was the first major theorem proved this way. It wasn't the last. Today, computer-assisted proofs and formal verification are increasingly common in mathematics. The Kepler conjecture on sphere packing was proved by Thomas Hales using massive computation, then formally verified in a project called FlySpec. Classification results in finite group theory rely on calculations no human has fully checked. Are we okay with this? Are we okay with mathematical truths that are in some sense too big for a single human mind? I think the answer has to be yes, because the alternative is leaving true things unproven simply because our brains are too small. And mathematics has never been about the limitations of the prover. It's about the structure of truth itself. But let's go back to that map for a moment. 4 colors, just 4. Out of all the infinitely complicated, wildly tangled, impossibly intricate maps you could ever draw on a flat surface, 4 colors will always be enough to keep neighboring regions distinct. There's something almost unreasonably elegant about that. A hard ceiling baked into the geometry of the plane itself, invisible until someone bothered to look for it, and then stubbornly resistant to proof for over 100 years. Francis Guthrie noticed it while doodling on a map of England in 1852. It took until 1976 for anyone to prove he was right. And even then, it took a machine to finish the job. The mathematicians who came after spent decades cleaning up, simplifying, and formalizing. And today, verified in Coq down to the axioms, the 4-color theorem stands as one of the most thoroughly checked results in all of mathematics. 4 colors, that's all you need. And now you know why proving it nearly broke mathematics in half.